today's speaker, Navinder Singh, really requires no introduction. Part of the KRL family. He's a trained electronics engineer who then switched to theoretical physics and obtained a PhD from National Research Institute of Physics. But of late, he's been passionate about something entirely different. For maybe about a year now, he is passionate about powered gliding. That interest then led him to examine the theory of flight and how aerodynamic lift is actually generated. So he's been looking at not just the history of flight, but also making some computations on how the lift is actually generated, and we're looking forward to that presentation today. So without much ado, let me invite Navinder Singh to present his talk today.
Yeah, so this is the topic, physics of flight, Bernoulli versus Newton, today's topic. And you know that air travel is quite common nowadays. And the physics behind the dynamics of flight is rather complicated. It's two contrasting situations. It appears that the field is well settled, but this is not true. If you browse the various explanations of the aerodynamic lift, there are conflicting arguments, explanations, and so this problem is there. And I have done some research in this field and found the correct explanation, and that I would like to share with you today. To begin with, let me start a little bit of background. My personal involvement with this field goes back to early 1990s, my school days. Your school days, my colleagues, my contemporaries, and you remember that is the time of one channel TV, that is Doordarshan, and the music in those days, for music the tape recorders were popular. This is a cassette, and so my interest, okay, of course, also was is in music, but along with what is important to me at that time was the electric motors in these tape recorders. So it was a hobby to collect these tiny small electric motors, and the purpose was to put them here in front of model aeroplanes. I used to make cardboard aeroplanes. This is not what I made, this is just taken from internet. My aeroplanes were rather cruder than this, and then I used to make propellers from these X-rays or some plastic sheet. You make a propeller, corkscrew type of arrangement, and then so initial things were rather trial and error. These guys used to run, but I was not successful in making a flying aeroplane. And later stages, I did some computations. I was quantitative, and I used the lift equation, which is half CL rho V square S, where S is the surface area of the wing, V is the speed with which the aeroplane is moving forward, rho is the density of the air, CL is what is called lift coefficient, it is roughly order of 1. And so I used this equation and measured the surface area, stuff like that. So what happened was the failure. So the reason was that motors were not powerful enough to generate sufficient speed to gain a required lift. So my aeroplanes used to run but not fly because of the heavy weight and less powerful motors. And then at the time, okay, I failed, so was a failure in making experimental flight, but then I was also interested in theory of the aerodynamic lift. So at the time, the argument was that, okay, the wind, the speed of the air is faster over the wing, over the top surface, and hence because the more speed, you have less pressure and you get aerodynamic lift upwards. The reason given was that the air parcels which they depart here, they have to meet here. So the parcels which go around the top of the wing has to move faster. So that reason was obviously flawed. I was disagreeing with that. And then an idea came to my mind, which was effective Venturi formation. So there is a sort of squeezing of the layers above the wing top surface, and this squeezing must be causing the high speed. Okay, so that is sort of 10th standard. And then what the problem was that because calculus, the calculus starts in +1, so I could not translate this idea into a formula. Then this hobby was then lost in orthodox academic tradition, time changed, and then recently last month I devoted 1 month, full 1 month just to aerodynamics. Actually I work in superconductivity theory, high temperature superconductivity, and this is a rather complicated problem, and after finishing a portion which is related to itinerant magnetism, it's one of the central piece in high temperature superconductivity. After finishing a piece of work, then I thought, let's take a break of 1 month from the mainstream field and work something totally different. And I started studying this aerodynamics, brought books and studied papers, downloaded literature, saw YouTube videos, stuff like that. And then, because obviously I am better prepared mathematically, I could translate that idea into an equation, and now we have an equation. And with Jerry and his student Sashi, we are trying to numerically solve it, and we are getting a preliminary results show that there is some truth in the equation. The idea of the equation I will tell soon along the course. All the what is fx, what is hc. So the point is that there is some length scale above the upper surface, okay, which is same for almost all airfoils, and if you know that hc and know the functional profile of the airfoil, you can calculate cl is the lift coefficient, which is the most important parameter in aerodynamics. Okay, along with this I am able to resolve the issues which I would like to share with you today.
Are you trying to say this 100 years nobody did this?
There are theories, there are formulas.
Space engineering,
Yes, there are formulas.
years.
Yes, over 100 years there are very sophisticated theories, and I will argue that my theory works at a zero angle of attack, and the theory which is now popular cannot explain this in a way which this theory can explain. That is the argument. I will come to that more
They
quantitative.
have been flying aeroplanes without that theory.
It is possible. Yeah, so it is true actually. In aerodynamics, the theoretical understanding is really poor. I have seen a very large number of YouTube videos of experts in the field, and I myself been interested in this from a long time, 25 years from onwards, on and off. And it is a truth that nobody understands how the aeroplane gain lift. It is a truth. Very few people have the correct explanation. That was Prandtl. If you talk to experts, they have differing opinions, and I will tell you what are the issues, why they differ, what is tricky in it, because everything is classical physics. It is Newton laws, Bernoulli theorem, fluid mechanics, but still the issue is complicated due to rather different reasons. Although it's not quantum mechanics, although not quantum field theory, but still there are issues in it which one should resolve it. Okay, we will come to the details, technical details of this thing. So this is the plan. I will start with a bit of history, various forces that act on an airplane, then what is the cause of the aerodynamic lift. Then there are two misconceptions. Okay, there are misconceptions that I classify in this way: Bernoulli's theorem with distance argument, then Newton's action reaction and push of the air from below. Then this is the correct theory actually, the Lancaster-Prandtl circulation theory. This is the correct theory at all angles of attack except the zero angle of attack. That I argue that a zero angle of attack, it has some gaps. The Lancaster-Prandtl theory. Then a little bit about the paragliding and powered paragliding. As Jerry told, I am recently interested in these things as a weekend hobby. Then the question is Lancaster-Prandtl theory is a complete picture? This is the question I will pose, and then I will propose this theory and then conclude. Okay, so bit of history. So I am going to very sketchy regarding the history, because in my last talk people said that I spent too much time on the history. So this time it is going to be sketchy, a little bit brief. But you know, any field, all scientific fields has a history, and it's always nice reviewing the history, and that gives you more motivation to study the field. So the history of this is extremely old. It's as old as the human consciousness. I mean, the people try to imitate birds actually, like making artificial wings, all sorts of things, and the recorded document, the actual careful drawings were done by Leonardo da Vinci, and he conceived the idea of ornithopter. somewhere between 1486 to 1490 in the 15th century. He was a painter of first rate and a scientist, philosopher. So this is one of his diagram, and it is something like you tie your arms here, there will be wings, and you do this flapping motion and it will gain lift. But I searched the literature, it is not known whether he was able to implement his ideas or not, but this was there in the literature. And then after 2-3 centuries the actual flight occurred in a rather different mode. This was done by Montgolfierd's brothers in 1783 in France, Paris. So they made a huge balloon, and it was a hot air balloon. So because hot air is lighter than colder air, and you get a buoyancy, and then it floated for roughly half an hour with 2 people as passengers. So this was first practical flying with the balloon, but it was not the fixed wing flying. The idea of fixed wing flying came with Sir George Cayley. The Cayley is one of the very first aerodynamicists, and he was the person who pointed out that inclined surfaces when moved through air can generate lift, aerodynamic lift. He performed the theoretical studies on aerodynamics, experimental studies. He made a what is this is called a whirling arm apparatus. It is the prototype of the wind tunnel, today's wind tunnel. So the idea is that you make a wing section and you fit it on one end, then you counterweight on the other, then with a string and a weight you rotate it. When it rotates, the wing rotates, and due to the angle of attack, the wing gains lift, and this whole lever tilts. And from the measurement of the tilt, one can calculate the lift generated. And he did such kind of experiments. He recorded, wrote papers and books on that. And the most important thing is he conceived the idea of the fixed wing aircraft. This is the idea, and he liked the idea so much because he wanted to have it permanent. He engraved it on silver disc. One side of the disc, this is his disc, silver disc, where he engraved it. So this is a fixed wing, and the wing is actually, you notice that the wing is not flat, it's a curved surface. So he knew that the curved surface can generate lift, and this is a vector diagram on the other side of the lift. So this is the drag, this is the lift, and he did the vector analysis late in the 19th century, and he was aware of the drag and lift, stuff like that. So it goes to very near to the modern understanding of aerodynamics. And then the practical, from theory to practice, the need to go into the air. So here is in the picture Otto Lilienthal. He is the glider man, the first glider man. He felt the need to go into the air. I will quote his wording. So this is his wording: one can get a proper insight into the practice of flying experiments. The manner in which we have to meet the irregularities of the wind when soaring in air can only be learnt by being in the air itself. So this man, he was a German engineer, and he devoted himself to the study of flight, and he did a lot of studies, first by just watching birds, and then he made gliders himself and collected the data, and he made gliders, and he also invented the stability criteria. It should have a tail, it should have an elevator, stuff like that, and he made over 2,000 successful flights from hills. He actually constructed one artificial hill near to his house, so that because the glider is to be launched in a direction opposite to the wind direction. So because if you have a artificial hill, you can launch in any direction, and we can say that he was the first airman, he was the first pilot who actually went into the air and learned its irregularities, recorded the data. And one unfortunate flight, he was met with the gusty air, the turbulence, and his glider stalled and he fell to his death. But he published his data, stuff like that, and later that data became the stepping stone for the Wright brothers. So here comes the Wright brothers, inventors of the first practical airplane. So building on the researches of the Otto Lilienthal, Wright brothers succeeded in making the very first powered, heavier than air flying machine. They opened a bicycle making company, and they were craftsmen of the first rank. They did thorough study of the existing aerodynamical literature. In addition, they did their own studies, tested over 200 different airfoil shapes in their own wind tunnel. So they constructed the wind tunnel, and the airfoil shape which we now encounter, actually they tested it. They found that the curved surfaces are more good to generate aerodynamic lift. And after building 3 successful unpowered gliders with increasing sophistication, they built their Wright Flyer 1 with 40 feet wingspan and 12 horsepower engine, every part made by themselves. So the Wright brothers' philosophy matched with the philosophy of Otto Lilienthal. So a general perception in the common public is that Wright brothers made a flying aeroplane, but actually they made gliders first. They trained themselves on gliders. They learned how to control the glider in the air. Only then they put the engine on it, and engine also they made themselves. And a very important thing is wing twisting idea to control the rolling motion. From the birds, actually they learned, the birds want to turn from the straight course, the bird actually twists his wings. So the wing twisting, by wing twisting you can imbalance the lift on 2 wings, you can tilt the aeroplane, and I will explain that this will you can turn on the plane using wing twisting idea, and this is what made what is called ailerons in the current aircrafts, and it is their idea. Through their persistent efforts, their detailed research and superb engineering, Wright brothers succeeded in building a heavier than air, engine driven and controllable airplane. This started the field of modern aviation. So here are the Wright brothers, Wilbur Wright and Orville Wright. So as I said, Otto Lilienthal sets the stage for them, and there is one telegram, original telegram with original misprints from Orville to his father on December 17, 1903. I will read it. This is the telegram written in shortest possible way. The success, 4 flights, Thursday morning, all against 21-mile wind, started from level with engine power alone. Average speed through air 31 mile, longest 57 seconds, inform press, home Christmas. So on 17th day, on the 17th December, they made 3 flights, longest is 57. This is the very first flight, and the picture, this picture preserves the most historic moment in the aviation history taken during the first flight, and this flight was very short flight. It just went up to 10 feet only, a couple of about 10 seconds it lasted. The third flight lasted for about 1 minute. This is their aeroplane, and here is the Orville lying adjacent to the engine. This is the details of their aircraft. So they have elevators in front of the plane. Nowadays these elevators are in the tail, and the rudder is in the tail. So now in current aircrafts, you know, the rudder and the tail and the elevators are at the back end of the aeroplane. So this is their design, and these are 2 propellers, and on one side of there is an engine, petrol engine, and so this is a craft which by itself took the speed equal to the flying speed, and it lifted off by itself, and by changing the angle of attack of these elevators and rudder, they can control its motion in air. And this is the first successful aeroplane. Okay, this is the end of my historical encounter of the history of aviation, but there were other people in the field like Percy Pilcher, Octave Chante, Sam Langley. These people also contributed importantly in the field. So I would like to move on to the more from the history to the dynamics and aerodynamics of the flight. So let us first discuss the various forces that act on an aeroplane. The question is, how do aeroplane fly? So it has many elements. One is the mechanism of lift. Then the aeroplane also, the pilots maneuver it, they control it, they turn it. You can land, you can take off, you can do so many things. So I am going to be again brief, and I am going to discuss only the central points. The most fundamental is this diagram. This is the aeroplane, and the thrust is generated by a propeller or a turbojet, and this propeller actually pushes the air backwards, and by Newton's conservation of momentum, not the rate of change of momentum is the force. So you get a force in the forward direction, which is thrust, and this thrust is balanced by the drag. Any body which moves in the air or a fluid experiences drag. So this drag in a level flight, a constant altitude, constant speed, the thrust equals to the drag, and the lift which is generated by the wings is equal to the weight of the aircraft. So when these vectors balance, you have a constant steady flight. So this is the main parts of the aeroplane. This view graph this lists some of the parts. So the central things is aileron, and these are used to turn the aeroplane. So I will discuss briefly how it is turned actually, and then the yellow ones are called flaps. This is called elevator. This is the horizontal stabilizer. Elevator is to control the pitch of the aeroplane, like the angle of attack, and this is a rudder, which the yaw 3-axis control. So the yaw, with the rudder you can change the nose of the aeroplane, you can turn it, but turning is little complicated. I will discuss it. So you might have noticed when the plane takes off, the flaps come down from the wings section, so that makes the larger angle of attack and larger wings area. So by doing so, the pilots actually make more aerodynamic lift at less speed, so that it can take off. And landing also, you need less speed and high aerodynamic lift, so the flaps are used while taking off or landing. This is the side view of the profile. This is the profile from the wing section. Actually, the upper curve is more curved than the bottom one, and the angle, this is called a chord line. The angle the chord line makes with the horizontal line is called the angle of attack. More angle of attack is more lift, and at a large angle of attack suddenly the lift starts to decrease. This is called stalling. We will come to that. So this is a one wing section. So I have some I have made just to you can pass on to each other. So this is from the, you can look at, you can from the various angles you see it, you feel it, but I am sure you must have noticed the upper surface of the wing is more curved than the lower surface, and that is very crucial in generating lift. We will come to that. So here is the diagram which shows ailerons in action. So this aircraft is turning. So the turning is achieved by lowering this elevator and raising this elevator. By doing so, you bank the aircraft. This is called bank. You bank the aircraft, and the lift actually acts perpendicular to the wingspan. Because of tilt, you have a component of the lift towards the center in this direction. Okay, vertical component of the lift balances the weight. This component, which is towards the center, provides the centripetal force. Because of centripetal force, the aeroplane moves in a circle. You turn it, but this turning is achieved also by changing the rudder. You change the rudder so that the nose also follows the turning. So this is the turning achieved by by changing the elevators. So this is the elevators, the ailerons. Sorry, the ailerons. If you turn it like, if you want to raise this side, you lower this aileron and raise this aileron. If you lower this, the lift will be more here and the lift will be less here, so this part will be going up. So this is the idea actually which was originally developed by Wright brothers, which is called wing twisting. So this is their, they patent it, and the aileron is their idea. So so this is the okay, there are other complicated maneuvers which aeroplane does, and those details we leave out for the moment for this seminar. Now we come to the main question of this presentation. Now the question is, what is the cause of the aerodynamic lift? This is the question which is extremely sort of, there are conflicting answers to this question. Let's reason it out, the proper answer. So to understand to get insight into the question, we have to first review Bernoulli theorem. I'm sure you everybody must be knowing Bernoulli's theorem. Just for refreshing your memory, I would like to revisit it in this just one slide. So Bernoulli theorem says that the pressure at say this point and the dynamical kinetic energy, which is a half rho V infinity square. V infinity is the speed say at this point, and pressure at this point is equal to the pressure at this, the speed at this. So if you simply solve it and along with the continuity equation, which says that the area of this section, which is A1, multiplied by the velocity, which is V1 here, is must be equal to the area A2 and multiplied by the velocity. This is true for an incompressible fluid, and for practical purposes we can treat the fluid to be incompressible, and because it is a narrow path here, the speed goes up. Now the speed of the fluid goes up, and then you can simply you can see it. If the speed goes up here, the pressure has to be lower here. This is a constant. Then if the speed goes up, the pressure has to be lower. So the pressure here is lower. If you see the gauge here, so this pressure is lower, this pressure is high, and then the speed goes slow here again, the pressure again goes high. So this is the essence of the Bernoulli theorem, and you can demonstrate it very easily. You just take a paper sheet and you blow over the paper. When you blow over the paper, actually you create a air current, and this current has more speed, and that's why you have less pressure, and due to less pressure the paper will lift automatically. But the actual thing is little bit complicated, because there is a viscosity of the air, there is a friction, and with this airstream the other air parcels will join, and there will be airflow below the paper also. So it's a little complicated, but this is roughly correct. And so you also have seen in cricket the fast bowler can spin, or the spinner can actually swing the ball in the air itself, or in football or in baseball athletes use this technique. So the idea is to give a spin to the ball. So when the ball is spinning and it's also having in a translational motion, then it turns sidewise. Why it turns? Because when the ball spins, it also spins the air around it because of friction. Because air has a viscosity, so due to viscosity the air near the ball also spins, and because it's also in flight, so on one side of the in this side you have more air speed, because these two vectorially add up, and in this side there is a cancellation of the speed, because this air which is rotating with the ball cancels with this air which comes this way. The net speed is low here, and the speed in this part is higher, and that by Bernoulli's principle, your higher speed here means your low pressure. So on one side of the ball you generate dynamically low pressure, another side you have more pressure. Due to this pressure difference you have force acting in the transverse direction. So the ball will be going like this, but it starts to bend in the right direction, in this direction. So the batsman will see the bending of the ball. Then suddenly when it touches the ground, then the spin becomes zero, because the rotational motion get dissipated when it strikes the ground, and the ball goes opposite direction. So it's just to confuse the batsman, or there are tricks which athletes use, and they use the Bernoulli principle. And this is the carburetor of your motorcycle, scooter. It also works on the same principle. Let's not go into the details of this. Okay, so now let me come to the standard explanation, which is generally available in the books. So standard explanation goes like this. So they argue that there is a more curvature on the top surface. So if you have picked two parcels, if you take two parcels, now the upper parcel has to go over a larger distance because it has a more curvature. The lower parcel is going straight. So since the upper parcel has to go a large distance, it has to speed up. If it speeds up, you get a more speed of the air current on the top of the wing, and the more speed in the top leads to low pressure, and you have a pressure difference, you get an aerodynamic lift. This is the standard reason given, but this is clearly wrong. Okay, the parcels which depart here never meet here. Okay, the parcel which depart here will never meet here. Actually the parcels which go on the top are always reaching before time. So I have a, oh, it is working in this, good. Now if you see this is a line of air parcels, these two parcels depart here. It's a computer simulation. So these parcels are going very fast. these parcels are going slow. Okay, so since these parcels go very fast, it leads to low pressure on the top, and you get a dynamical lift. Okay, so now why the air parcels on the top of the wing goes fast? This is a question which was answered in the circulation theory of lift, which is the actual theory of lift, which is the correct theory of lift. But in the literature there is an alternative explanation. So the alternative explanation says, which is really very close to common sense, it says that the air, because the wing section is at an angle of attack, so when it is an angle of attack, the air which strikes, it will be deflected downwards. The air is striking like this, deflecting downwards, and then by action and reaction, so there is a upward force acting on the wing. This is wrong. If you use this Newton's action and reaction and you calculate how the force varies as a function of angle, you get it is proportional to sine square theta. It is never observed in experiments. Experiments, it is proportional to theta, not sine square theta. So it disagree with experiments. Number one. Okay, so in other words, the lift is generated. Okay, the push of the air from below. So Newtonian explanation is wrong on many accounts. In this theory, the lift is proportional to the angle of attack squared, not linearly proportional to the angle of attack as observed experiment. This is already I told you. Airflow is not like bombarding bullets. Upper stream is also deflected due to fluid motion. So what is important, one misses, is that okay, if you have bullets and they strike here, they will definitely deflect. But the fluid is not bullets. I mean, the fluid motion is, it has its characteristic fluid properties. Even the upper air streams do deflect downwards. So so that is missed in this explanation. That is very important. So calculated lift slowly due to this is too less, and definitely if you take a simple sheet and you just push it, due to Newton law there will be a lift generated, but that lift is just minor. It is just 5% or 10% total. The main component of the lift comes from the suction due to Bernoulli principle, and the reason for that given in the standard explanation is wrong. The reason is different. That we will come to that soon. So in other words, the lift is generated due to, okay, so this we have already. Now it cannot explain the value of lift at zero angle of attack. If you use Newton theory and you just take a wing section at zero angle of attack, then there is no way the air can be deflected downwards. But there is a finite value of lift even at a zero angle of attack. So the Newton theory, this explanation has to be abandoned. There is a problem with this explanation. Okay, let me summarize this part of the discussion. So there are two schools of thought. One is the Bernoulli principle using distance argument. So they say that because the distance over the top is more, so air parcels are not living beings that they have to depart here, that to meet here. So this is clearly wrong. And then another wrong explanation is that the air is deflected from below the wing. If this is true, then how a lift can be generated at a zero angle of attack? So this is also wrong. Okay, so let me come to the correct explanation. This is the explanation which is called Lancaster-Prandtl circulation theory. It was given in 1920s, but if you study current literature, I don't know why they missed this explanation. I have because nowadays you can download the original literature from the websites in the internet and the books and stuff like that from Russian website. I downloaded this man's work, and it is very clear in their minds. All these mechanisms, stuff like that. Okay, at zero angle attack there is something missing in their mechanism, but this is the true mechanism of the aerodynamic lift. These guys pointed out to the correct explanation of the Lancaster-Prandtl circulation theory. So these are the steps we will follow: starting vortex generation, Helmholtz theorem, vortex anti-vortex pair generation, induced circulation around the wing profile, and Kutta condition. He was a mathematician who contributed to the theory of lift. Induced circulation and increased speed on the top of surface of the wing, Joukowski-Kotek theorem, which relates the circulation with the lift. So generally these things are seen as highly complicated. Maybe that's the reason it is avoided in general discussions, but they are not complicated. They are very simple. I am going to show you. These ideas are really common sense actually. Now a little bit of these two men. Here is Ludwig Prandtl, one of the most famous aerodynamicists of 20th century. You might be knowing about the boundary layer theory and the lifting line theory, and it was generated by it was his inventions. They are the gems in this field of aerodynamics. The boundary layer theory is actually takes into account the viscosity of the air. Very near to the wing section, the air molecules are actually still. So there is a boundary very near to the surface of the any body, any body which is moving in the fluid. In the near to the surface, it is at rest, but afterwards, and because of viscosity, the other layers move with speed. So there is a boundary layer that was he discovered, and he contributed many other things along with the correct explanation. And he is Lancaster, English polymath and engineer, developed the circulation theory in 1907. These guys met actually. They independently have the similar ideas, and this person spoke English, and this was a hardcore German guy, and they could not communicate. But somehow, I mean, later on, now there are debates. Okay, Prandtl was the originator or the Lancaster was the originator, but generally it is good to say Lancaster, Prandtl circulation theory both contributed, and there are other two men also contributed in the theory. So there is a nice history to this this subject. We will skip that for time. Now, so I would would like to go into the correct explanation. This is the starting vortex generation. So the idea is that when the wing starts, actually it generates a vortex at the tail. This is called the starting vortex. Now if you see, now this explanation is also not known. Even there is a book by Anderson on aerodynamics. He is the authority in the field. I read his book very carefully. He also not able to explain why there is a vortex at the tail. I think the reason is this, which I think is the correct one, because at a finite angle of attack you get effective venturi formation at the tail, below the tail, and this makes the more speed of the air streams, air parcels which come from below the wing, because these guys are moving faster, upper guys are moving slow. The wind tries to curl up, and it curls up, it generates a starting vortex. Okay, I have a video which shows this. Now how to can I can you click on this video? इसके ऊपर नहीं चलेगा ना? इसके ऊपर video. This one. Yeah, can you bigger screen? Okay. So this is the experiment done by Prandtl himself. So they have an aluminium powder. Okay, they have a wind tunnel, and then they put aluminium powder, fine aluminium powder, to visualize these air streams. So you have wing section. Now it starts. You see here. So there is a circulation generated, and there is a counter circulation also generated. There is a series of vortices formed. So this is a clear demonstration of Helmholtz theorem, which I am going to explain to you. Helmholtz theorem says that if you have a vortex, there must be anti-vortex, because net vorticity in a fluid, undisturbed fluid, must be 0. So this is a vortex, and you see anti-vortex forms here. So due to the anti-vortex formation, the wing of the aeroplane actually like a ball which is spinning. So you get a more speed on the top of this because of circulation. So these experiments clearly show the vorticity. This is written in German. I don't understand it. So this is one more experiment. So this is the starting vortex, and if this vortex is there, there has to be anti-vortex around the wing section. I don't know what happened to this. Maybe it's the problem with the downloading. So there is a problem in downloading actually. So this is the two vortices you see. One is vortex, we can just switch off, the video is not downloaded properly, but I hope you got the idea that there is a vortex formation and there is anti-vortex formation. No, okay, I will do it. Yeah, thank you. Okay. Yeah. So the point is that so the point is that if there is a starting vortex, there is an anti-vortex form. This is by Helmholtz theorem. So it's like two gears. One gear rotates this way, another gear has to rotate opposite way. Now if there is a circulation of the air around it, if there is a circulation and you superimpose the translational motion due to the forward speed of the aeroplane, these two air streams add up, okay, and you get a more speed on the top, but this is going forward, this is going backward, they cancel partially and you get a low speed on the bottom. This is the reason you get a high speed on the top, low speed on the bottom, and due to high speed you get a low pressure by Bernoulli theorem. Then the Bernoulli theorem can be consistently applied. This is the main the correct explanation of the theory of the lift, suction lift by Bernoulli theorem. Now since the wings of the aeroplane are not infinite, they are finite, at the tips of the wings the air tries to enter into, because you have low pressure on the top, high pressure below, so the air parcels try to come up and go on the top. Due to this a curling motion starts. These are wing tip vortices. So you get air going down from here. So when the plane flies, so you get the air pushed downwards from here and from here. So that's called downwash. So huge amount of the air current is pushed downwards by the aeroplane, and if you calculate the total momentum transfer downwards, and from the momentum transfer per unit time you can calculate the force, and that must equal to the force, the lift force, because the conservation principles must be valid. Okay, so that is the explanation of the aerodynamic lift, the correct explanation of the aerodynamic lift. Now there is one subtlety involved here. So the lift force actually goes higher and higher. You see at zero angle of attack is the angle between the chord line and the horizontal line. So when you increase the angle of attack you get more lift, okay, but at some point the stall occurs. So so the point is that this is at zero angle of attack. You increase the angle of attack, the flow starts to separate from the wing section. So once it separates completely, you get a turbulence on the top of the wing section. So due to this turbulence there is a sudden loss of pressure, the suction goes away and you lose the lift, aerodynamic lift, and this is the major cause of accidents, the crashes. Because of this is the real fluid flow, so you have a lot of turbulence on the top of the wing. This turbulence can kill the lift, and this can happen. So there was an accident happened on the French aircraft, I think 12 years ago, I am exactly not remembering. So the thing was that they were flying with the autopilot mode, and due to ice formation in the pitot tubes, the computer was not able to read what is the airspeed, and so the computer started decreasing the speed of the aeroplane. It was a jumbo jet with more than 200 passengers, and that plane started to slow down, and then they noticed that the plane is slowing down, but it lost a lot of altitude. The pilots actually made a lot of angle of attack without putting the enough speed, and then this stall happened because at large angle of attack you get a turbulence on the wing, upper surface of the wing. Because of this stall happened, it just went into the ocean and everybody died. So this is really tricky. One has to be very careful about in flying what is the stall speed of the aircraft. The stall occurs because of this flow separation, and this is one has to be practical flying is the issue, the main issue. Okay, so this is a mathematical formulation which I would not go into this colloquium level talk, but technical, if somebody is interested, I am happy to help in this. So this is called the Kutta-Joukowski theorem, which relates the total lift in newtons is equal to the circulation. Circulation is nothing but the line integral of the velocity along the contour drawn along the wing section, and then in in this theory. So the total circulation is divided into microscopic circulations integrated over the whole chord line, and one can drive this with some there is a lengthy calculation. This is the final result. It is the integral equation. This dz is the functional profile of the wing section, and v infinity is the speed at far away from this thing. C is the length of the wing, width of the wing, this is called the chord length, and by solving the integral equation you can calculate gamma, and the lift can be calculated. These computations people do routinely to design wing sections. So to summarize this part of the talk, number one, many misconceptions which are generally found in the literature in the explanation narrative are clarified. These misconceptions are related to the wrong application of the Bernoulli theorem, distance argument, and Newton's dynamical laws pushed from below in the mechanism of aerodynamic lift. So you see, notice that. So this argument that air parcels depart here, they has to meet here, and then the parcel in the top has to go faster because it has to have a cover a more distance is wrong, because air parcels are not intelligent beings. So this is wrong. And then the air deflected by the lower surface is also wrong. The correct explanation is this theory of the circulation theory. Because of the circulation, you have more speed on the top surface, and that's why you low pressure because by the Bernoulli theorem. This is the correct explanation. Yeah, sure. It is laminar flow. It is the laminar flow. Yes, atmosphere, that's a good question, but once the airplane flies, the flow over the wing is laminar. If it is not laminar, if it is turbulent, you will not generate lift. I will come to that. Because you can get a lift, because for example airplane when it takes off, it reaches 300 kilometers per hour speed. On the runway, the speed is roughly 300 to 250, roughly that speed. So even if it is thunderstorm, it's raining, there are winds of 40 km per hour. 40 km per hour wind is, atmospheric science, it's a huge wind. So 40 km per hour and 300 per hour, 40 km per hour is nothing. For these jet aeroplanes, because their sheer power and their shape, and their speed, these turbulences are nothing. And we generally, when we fly, you get turbulence. The turbulence is actually what you are saying is correct, because the atmosphere is not nice laboratory. There are always currents going up, hot air going up, cold air going down, cloud formation, turbulence in the air. We do get turbulence, and then generally the pilot announces, please put on your belt, buckle your belt, but the turbulence is not harmful. It occurs because the aeroplane goes from a region where the air current is going up, and suddenly it enters a region where the air current is going down. So there is a little fluctuation of the lift, and it gives jerks, but nothing happens. It can't tilt the aeroplane. The turbulence over the 100 years, there is no single accident due to turbulence of the atmosphere.
This theorem, you can have plane, why we need this shape of the wing? That is not coming into this theorem. You can have simple cardboard.
Yes, simple cardboard. Yes, a very good question. Yeah, a simple, a flat plate like this will also have a circulation. Now the problem is that if you take a flat plate, if this is working. Okay. So the problem is that if you take a flat plate like this, if you have flat plate, then the wind will have to go like this. So this is the streamlines turning downwards. This guy is okay. Now the thing is that because it is a flat plate, okay, not the peculiar shape which I showed the wing profile. There is a detachment of the streamline from the surface of the wing. That detachment occurs at the leading edge itself. So at a small angle of attack, this is good, but little bit you increase the angle of attack, detachment starts, and it will stall at a very small angle. So that's why the flat plates are not very good airfoils. They are dangerous. So they are good at small angle of attack, but not a large angle of attack. But if you have a wing like this, if you have a wing profile like this, because of its nice rounded shape, so detachment which is shown here, this detachment is delayed. If you have flat plate, then detachment occurs here, but this kind of shape, detachment of the of the laminar flow is delayed, and you can have a safe flight even at a large angle of attack. But it has also its limitations. I mean, at some point it's going to break down.
I have to, in this section I have two questions.
Uh,
What is the continuation of, this is very similar to what Anish asked. My doubt is that whether is the same concepts of lift theory,
uh,
the equations and everything, is it same for different wing profiles? For example, Concord delta wing.
yeah, okay, so this is subsonic flight. So whole talk is subsonic flight. Once we reach supersonic, when the speed reaches the speed of sound, the physics changes. It's supersonic. This theory doesn't apply there.
No. We are talking about only lifting, the initial lift.
Yeah,
This is the whole thing is about initial lift.
lift, right. Yeah, that's right.
So why should it be different for
Start from
Supersonic speed, any surface provided.
has to work on subsonic.
Yeah, yeah.
Surface will provide lift at supersonic speed.
Yes, right. Yeah, that's right. That's right. Yeah.
That is not at supersonic
That
speed.
is why for supersonic aircraft you need to have, for example,
Yeah.
planes have this
This ones. Yeah. So
No, the thing
the wings come.
is lift. How do they get lift? So
The same Bernoulli principle, they left the Bernoulli principle, but this theory is not applicable. This theory here, the circulation theory, that is not applicable. It is the Bernoulli principle only. The pressure has to go up, the suction lift. But the theory, this is not the theory which is directly applicable to the supersonic speed, because
when you are going supersonic speed, it attains at a particular height.
Huh.
When they go at
yeah, but when they start,
that is
huh,
true.
so then the theory is applicable. This theory is applicable. Yeah.
So
supersonic planes have this.
he is asking the wings are not like the same wings.
Then wing shape has to be changed.
Planes don't have same wings.
Yeah, wing shape has to be changed. There are many reasons of that. Number one is the shock.
My question is to be precise, are the design considerations that
Yeah.
from physics to engineering,
Uh-huh.
design considerations
Changes
are
actually.
they identical or
No, they are not actually. If you look at the supersonic jets at say Mach number 2, their wings are okay. I don't have the picture for them, but their wings are not fat actually. They are very thin. If you look from the side, so their wings will be like this, very very thin, and their leading edge will be sharp. So the sharp like an arrow, it has to penetrate into the air. If it is blunt actually, like in this case at subsonic speed, there will be a huge air drag, and that will cost a lot of energy. More powerful engines, it won't work actually. The jet air, which supersonic, so it's just like a flat plate, as Jerry said, I mean, because it has to just penetrate into the air, and at a speed of say 1500 kilometers per hour.
They can
Yeah.
get a lift within hundreds of meters.
Yes,
Those are on the ship.
because
In
the
100 meters they get lift.
yeah, because the speed, sheer speed, because this is the speed. The lift is, yeah. So no, the mechanism is the Bernoulli principle only. No,
But they are lift.
their lift is the mechanism, the Bernoulli principle, but the wing shape, as Subbu was asking, the wing shape is different. It's more streamlined actually. It's not fat, because the fat wing will generate a lot of air drag, and because the speed is large. Now you see the lift is proportional to V infinity. If the atmosphere is still, let's say it's a no wind condition. If the atmosphere is still, this is the speed with which the aircraft moves forward. Like during takeoff, 200 kilometers per hour. So this is 200 kilometers per hour. In case of the supersonic things, this speed will be 500 kilometers per hour, just after a couple of seconds, minutes after the flight. So you definitely have a more lift. But to counter, you need less circulation, so the wing shape is changed. So this wing shape, this whole thing, this discussion is subsonic regime, and supersonic, the physics, the wing sections has to be changed, and actually my knowledge is not very good in supersonic thing. So rather than saying wrong, I should admit that my understanding of supersonic aerodynamics is not good. Sure.
Like he said, even a supersonic plane has to take off from zero velocity.
Yes.
It has to have some kind of a cambered shape.
Camber, some kind of little camber.
Supersonic velocity, the cambered shape produces drag rather than lift.
Right. There should be less camber rate. Less camber rate.
Other things to
Others are right. Yeah. Less camber rate. Yeah.
variable geometry wings, they have swing wings, all kinds of
Right. Right. But what I can say is that lift has to be generated by Bernoulli principle. The suction lift, which is little counterintuitive, but you see the air pressure is one Grulich experiment. You know, You take a steel half semispheres and he removed air from this, and it's extremely difficult to. The air pressure is very deceptive. I mean, it's not visible apparently, but little bit of pressure difference generates a huge amount of. I mean, the jumbo jets, huge tons of weight. It easily lifts, just suction lift. Okay.
One more question.
Yeah.
That is regarding the turbulence.
Yeah.
Along the trailing edge in the turbulence that contribute to circulation, stability, principle that you explained. But on the edge,
Uh-huh.
edge of the tip of
Correct.
the wing, there is another turbulence which is actually it will drag. It will contribute to the drag.
Okay. Pressure drag. That is there actually.
So the spoiler mechanism, etc.
Yes. Right. Yeah. Yeah, so sometimes now you have seen what is this new Air India introduced a new. Yeah, they turn the tip upwards. So by turning the tip upwards, so you shed the vortex. Number one, you reduce the strength of the tip of vortex. Then you shed it in a way which reduce the drag. Actually, this creates a drag, and it is not useful. So in many aeroplanes they put a plate, flat plate, so that you can reduce these tip vortices, or the wing tips are folded upwards. It has a lot of physics in it, which I am not expert in that, but roughly the purpose is to reduce this wing vortices. Spoiler designs are also there to reduce the turbulence, right? Yes, there are there. The spoilers, yes, the spoilers are there actually. Yes, maybe we can discuss this technique. I have read it. Spoilers, I have read it. Yeah, but yes. So there they use these devices to reduce drag and increase lift. Yeah. Okay. So now let me turn to another field. Just couple of slides. I will finish in 10 minutes, 5-10 minutes. So physics of paragliders and power paragliders. In my opinion, this is the simplest aircraft ever devised. You can pack in a bag. I have one. This is, you can pack in a bag, just this much big bag, and the thing is that it's a nylon, very tough nylon fabric, and there are nylon lines, and they are connected to various parts of this. They are very strong. Each line can withstand more than 30-40 kilo, but the weight is shared between the lines, and this has openings. This is called a paraglider. You take this. These are the lines, and it's called risers, stuff like that. It is attached to the harness, and you run it by taking this thing. It's like a parachute. When you run, actually, due to the air, it inflates, and air enters the cells. It inflates, and it takes a shape of a wing. Its upper surface is more curved than the lower. It's just a airfoil, and then by controlling, you can control the shape of this. You can change the angle of attack just by pulling the lines. So, but you should know which line is to be pulled. So you can change the angle of attack. You can change the lift. You can change the drag. You can turn this. So if you pull these lines, this tip will be little. It's like a wing swapping, wing flipping, or wing twisting. You twist one tip, you get a drag on one side. You turn it. You can maneuver it. It can be controlled, and okay, so let me come to this. Is one flight, for example, it's called ridge soaring. So this fellow runs down the hill, and so the wind is coming in this direction. So you have to choose a particular location on a hill where the wind is coming towards you. You run into the wind, and it inflates the paraglider, and it lifts you. Now there is no power. There is no power. The thing is that the wind is coming. If the wind is coming this way, this photo is taken at Bir Billing in Himachal Pradesh. So if the wind is coming this way, it rises up. So this uprising currents, with the uprising currents, the pilot can gain lift and go up to thousands of feet, just using the air currents. And definitely it's a glider. It comes down very slowly, and for 6 feet go forward, 1 feet comes down. Then one has to learn how to find. So it is just. One should have a good understanding of the atmosphere, where the air current is going up, where it is going down. So you have to stay in an area where the air is going up, and that way you can exploit this thing and enjoy the flight. So let us not go into this how it works. Actually, it also generates, in the same principle, it also generates aerodynamic lift with the circulation, and the lift will have a component in the forward direction which takes it forward direction. So let's not go into this. Now there is another way. So this paragliding is done on hills, but there is another variation which is called power paraglider. So in this you actually literally tie a engine in your back. I have one engine with me. I do this, and then it's a petrol engine, 2-stroke petrol engine, some 30 horsepower, and you run it on a flat ground in a gentle atmospheric conditions, gentle winds like 10 km/h, and run into the wind. You switch on the motor, and the propeller here rotates, and it gives you thrust in the forward direction, and it's just a simply aeroplane, and you can fly. The people flies for hours using this, and it can go up to 5 kilometers, but there is no need to go that high. And air regulations has to be satisfied. One has to be away from airports. All those conditions are there. You have to do in open grounds, open places, not public places, stuff like that. This is one thing. Now little bit of atmospheric science is worth reviewing here. How these guys actually fly. So these guys fly by looking at the currents. I mean, my atmospheric colleagues will be knowing much better than me here. So when you have a cloud field, it generally becomes hot during the day. You get a hot air rising from here. Then you have a marsh. In the marsh, actually it's a watered surface. So there the temperature is less, so the wind will come down. Then you have township, like the buildings, the concrete structures heat up with the sun, and you get a hot air going up. So the paraglider pilots, what they do, they look for the thermals going up. So they enter into a thermal, then like you have seen kites or eagles flying out there. So they always circle. I mean, you might have wondered why they circle. Because they find a thermal there. Okay. For example, if you look from the window from this main building and you look towards GMDC ground, you can always find eagles there. There is no fish in the GMDC ground, but the ground is open, and at 11 o'clock or 12 o'clock it becomes hot, sufficiently hot, it generates a lot of thermals. And these guys actually look for thermals, and they keep rotating in the thermal and gain high altitudes just due to thermals. So the paraglider pilots, they gain height, and because the thermal actually dissipates when it goes up, it becomes a cloud, because the temperature goes low when you go high in the atmosphere. At say 3-4 kilometers, this thermal condenses to make a cloud, and then the cloud drifts. If the cloud is on above a marsh, the cloud will decay, and this is the atmospheric, the low Earth atmospheric science. But these thermals are really useful for the unpowered flight, but for the powered flight they are not good. For example, we generally sometimes go to Bagodra. It is some 60 kilometers away from here. It's the other portion of this Nal Sarovar river. It's a bed, and in the summer it becomes hot. When you fly with the power paraglider, when you try to enter into this, so like 50 feet or 100 feet, you get air bubbles. They are not visible, and again, or location knowing better than me. So these air bubbles are not visible, but when you enter into it, they cause a lot of disturbance because it's a turbulence. Okay, I should say that I mean, one has to learn it properly for safely. It's a very safe sports actually, but one has to learn it properly to do this thing. Okay, so and actually we do it. If you are interested, you can contact me. We have a WhatsApp group called Peasants of Paragliding. This is my photo. This is my glider. This is I'm practicing in the riverfront. Sometimes on weekends, and when there are holiday, we go once in a month or like that. But this is not the good weather. So weather starts October. This is monsoon weather is bad. Hot summer is bad because a lot of thermals is not good for these gliders. So October, November, December, January, February, for 4-5 months is nice activity. It's a sports activity, and if you are interested, you are most welcome to join this. Okay, so coming back to the theory of the aerodynamic lift, the question is, does Lancaster-Prandtl theory provide the complete picture? This is the question which is certainly important, because if at a zero angle of attack, I don't understand how a vortex can form. Because you see, you notice that in the vortex formation theory, where the vortex is formed, it is always at angle of attack. Because of the angle of attack, you have an effective venturi formed here, means a narrow path a narrow path formed here, and the airspeed is more here, less there, it curls up, you get a vortex. But at a 0 angle of attack, there is no way that you can get a vortex formation, but you do get a lift at 0 angle of attack. Then what is the reason? So
Who gets a lift at 0 attack?
all wings, all cambered wings get a 0 at 0 angle of attack.
No, all aircraft you see they keep at an angle.
Yeah, they keep at an angle, but if you take a wing section, put in the wind tunnel and put a balance, you measure it, you get a lift. In the experiment, you see the lift actually in the controlled experiment. So my idea was to have there is a certain characteristic length scale of the top, and using the Bernoulli principle and continuity equation, so I came up with this equation for the lift coefficient. Okay, now with Jerry and his student Sashi, so we are actually taking a lot of wing sections. NACA has a tables, some hundreds of wing sections they have studied. So we are actually Sashi is taking from the data the CL numerically, he is taking CL, and he is fitting the profile with a function, let's say polynomial function, and that polynomial function goes into here, and this integration is done self consistently. We have a program for this. We are doing these integrations, we are calculating HC. So I have done a preliminary calculation which shows that HC, this HC which is computed self consistently from this equation, divided by the maximum height of the profile, is constant. It comes roughly, for this is Rode wing sections, the name of the wing section. For this it is come 3.3 within 10% variation. But Sashi has done for 8 profiles, he saw that HC is rather coming the same roughly, with some standard deviation of 0.05, with the value of what was that value, Sashi? 5. Value of SC is 5 and the standard deviation is 0.05. Is it true? Yeah, so it's rather stays constant. So if we extensively do a numerical analysis, and then we can say that this kind of family of wing profiles HC is given, then what one has to do, one has to just design a airfoil with given functional profile fx, you plug in this equation, do the computation, get CL. CL is the lift coefficient which stays in here. I mean, in the lift equation, the written, I forgot to write it here, but it was written in the very beginning slide. So you put the CL there because CL is the main coefficient which is not known. It is to be computed theoretically. So for example, the very beginning equation, the CL comes here, this is the lift coefficient, rho of the density of the air, you know, velocity, you know, with which the aircraft moves, wing area, all these design parameters, stuff like that. So the point is that we have a formula, and so the initial numerical results show that there is some truth in this equation at 0 angle of attack, and need is to develop it at a finite angle of attack. Now I don't have so it was just 1 month sort of detour from my mainstream topic of condensed matter physics. We'll publish couple of papers and then leave the topic. So this, if you want to consult, you can consult these references right here. Thank you very much. Questions? No. Yeah, f of x is the function of the height of the upper surface of the airfoil as a function of x, the chord length. Right here.
So now my question is that how do you make sure that there are no chords in the function?
How
Chord, COL.
no, this is just the literally. I mean, this is this fx.
I will tell you why,
fx.
why I am asking this question, because this hard-shell scattering it is called.
Uh-huh.
Circular scattering.
Uh-huh.
It is long back. The order this one. The procession can be derived from the geometry of the shell. It is just taking the motion transfer on a hard shell.
Okay. Right.
The molecular scattering.
Right. Yeah.
So actually there is a transformation equation is something like this. And the
Correct.
topological, is the mapping of the topology.
Correct. Right.
There
Yeah.
are this
Poles.
function passes through external. Thus the condition
Hmm.
valid as there you have problems.
Yeah, because those complications could arise because this is the shape of the wing viewed from a sideways, but the airstream. Yes.
Where you are putting this function of x there, this is equal to big contour.
No, no, because there is no divergence in this formula. Maximum, the HC is much bigger than the maximum value of fx. So fx is this much, suppose it's 1 unit, but HC is 4 units. So this denominator is always positive definite because the square is there, it's a positive definite. So the integrand is convergent. There is no divergence in the integrand. The integral is finite. But if HC is less than maximum value, if that turns out, then there is a complication. But
The differentiability of x.
yeah, but if HC is less than the maximum value of the fx, then at some point when HC is equal to the fx naught at that particular x naught, then there is a problem, there is a divergence. But so far we have studied HC comes out to be bigger.
Here there is some region where d of x is equal. I don't know whether it is relevant here because since I have encountered a similar problem elsewhere.
Yeah.
That's why I'm asking.
Yeah, but here I think this problem is not there. But I have to understand this thing, what you are saying right here. Yeah. Thank you.